Imagine you're sitting at your computer. It's late, you're tired, and you've just run a parameter sweep on a new algorithmic trading strategy.
Oh, the classic late-night data grind.
Yeah, exactly. Let's say it is a relatively standard moving average crossover model. You decide to test 16 different fast lengths against 40 different slow lengths.
So that's 640 combinations in total.
Right, 640. You hit run, the computer churns through the historical data, the grid finishes, and suddenly one single cell on your monitor glows bright green.
The cell everyone is desperately looking for.
Exactly. It shows an annualized Sharpe ratio of 3.9, and right next to it, the ultimate validation in standard statistics, a p-value with 12 zeros of significance.
Wow.
Yeah, we are talking 6 times 10 to the negative 12th power. I mean, the software is essentially screaming at you that this result is mathematically undeniably real. You think you found the Holy Grail, you know. You think you have an edge on the market.
And here is the core, really chilling premise of our source material for today. You probably haven't found anything at all.
Wait, nothing.
In fact, you almost certainly haven't. See, a parameter search is not actually a test in the way classical statistics taught us to think about tests. It's a machine.
Okay, a machine.
And it is a machine specifically designed and calibrated for manufacturing luck. All it does is find the luckiest outcome out of n tries.
And it doesn't care if there's actually something real there.
Exactly. It will find a lucky outcome, whether there's a real underlying edge in your logic, or if you are literally feeding it pure, unadulterated noise.
And that is the illusion we're going to dismantle today. Welcome to the deep dive, everyone. We are pulling our insights from a really deeply rigorous paper titled Backtests Without Illusions, Pricing the Search for Alpha.
Specifically, we'll be zeroing in on the mechanics of something called the Deflated Sharpe Ratio.
Right. The mission here is to protect you, the listener, from one of the most expensive traps in quantitative analysis, data science, and honestly, just applied human logic.
It's a massive trap.
It really is. So we are going to look at how standard statistical tools lie to you in these scenarios. Then we'll explore the mathematical cures that actually fix the problem.
And finally, we'll dive into a real-world trap where even those cures break down if you don't know how to read the data.
Let's jump in. To really understand the depth of this trap, we have to start with a perfectly controlled experiment. The authors of the paper, they don't begin with messy real-world market data, right?
No, they don't. Because if you use real data and your strategy fails, you never know if your statistics were just too harsh or if the market simply shifted.
Right, there's too many confounding variables.
Exactly. So they build a synthetic environment. They generate 1,000 trading strategies using pure, independent, standard normal noise.
Let's define exactly what that means for you guys listening, because standard normal noise is a term thrown around in Stats 101, but in the context of a trading strategy, it has, well, profound implications.
It really does.
It means every single simulated day, the return of the strategy is drawn from a bell curve centered perfectly at 0, with a standard deviation of 1.
Meaning there is zero drift.
Zero drift, there is no hidden momentum pattern, no mean reversion, no actual skill. It is the mathematical equivalent of television static.
Precisely. It's just static. Because it's pure static, the true underlying Sharpe ratio, which, is how we measure risk-adjusted return for every single one of those 1,000 strategies, is exactly 0.
By definition, there is absolutely no edge here.
None. And they give each of these 1,000 strategies 1,000 observations, which you can think of as 1,000 days of trading.
So we essentially have 1,000 monkeys throwing darts at a board for 1,000 days.
Yeah, that's a good way to picture it.
And then we do what every data scientist, every quantitative researcher does when they run a parameter sweep. We ask the computer, hey, just keep the best one.
The single best performer.
Right. So what actually happens to the numbers when we isolate that single best performer out of the 1,000 pure noise strategies?
Well, when you isolate just that maximum strategy, its per observation Sharpe ratio averages 0.1027.
Okay, 0.1027.
But in finance, we don't usually look at daily Sharpe ratios, we annualize them. To annualize a daily Sharpe, you multiply it by the square root of 252, which is the standard number of trading days in a year.
Right.
When you do that, that 0.1027 becomes an annualized Sharpe ratio of 1.63.
I really want to pause on that number because we need to ground it in reality for the listener. An annualized Sharpe of 1.63 is a phenomenal result.
Oh, it's incredible.
If you run a fund with a legitimate long-term Sharpe of 1.63, you are getting written up in the financial media. You are attracting billions in institutional capital.
You're a star.
Yeah, it implies an incredibly smooth, consistent upward climb in your equity curve. And in this experiment, that exact profile is being generated by a random number generator with the dial explicitly, provably set to 0.
It is an illusion created entirely by the act of selection. And to understand why standard statistics fails to catch this, you have to look at what happens when you feed that purely lucky 1.63 Sharpe ratio into a standard significance test.
Right. This is the exact test your Python or library will run if you just, call a basic statistical summary function.
Exactly. It takes the Sharpe, converts it to a t-statistic, and calculates the one-sided p-value.
The software looks at the 1.63 and basically asks, what are the odds of seeing a number this high if the true underlying edge is 0?
And for these pure noise winners, the median p-value comes back as 0.0000686.
Wow.
3 zeros of strict statistical significance generated from literal static.
Which brings us to the false discovery rate, the FDR. The researchers didn't just run this once, right?
No. They ran this entire experiment, generating 1,000 noise strategies, picking the winner and testing it 2,000 separate times.
So that is 2,000 independent null searches.
And out of those 2,000 searches of pure noise, the naive test declared a mathematically significant discovery every single time.
That's insane.
The false discovery rate isn't just high, it is 10000. It is 100% guaranteed to be wrong.
Let's break down the mechanics of why the standard test is lying to us so aggressively here. The naive significance test is asking a very specific question, right? Could the Sharpe ratio arise by chance under the null hypothesis?
Yes.
And to be fair to the math, that is a perfectly rigorous question if and only if you are testing a single pre-register hypothesis.
Right. If you woke up, wrote down one single strategy rule, tested it once, and got a 1.63, then yes, the p-value of 0.0000686 is totally accurate.
But that is not what you did.
Not at all. You conditioned your test on the maximum of a search. When you take the best of 1,000 draws, the underlying sampling distribution fundamentally changes. The math, built into standard software, assumes it is evaluating a single random draw from a normal distribution. But the distribution of a maximum is nothing like the distribution of a single random draw. It is shifted heavily to the right.
I actually think of it like an archery competition, but with a twist. Imagine you have a person who has never shot a bow in their life.
Okay.
You put them on a field, blindfold them, and ask them to shoot an arrow at a target. They shoot one arrow. It lands nowhere near the bullseye. That's a single test.
Right, that's the baseline.
Now imagine you put 1,000 blindfolded amateurs on the field, and they all shoot one arrow at the same target. By pure geographic chance, one of those arrows is going to land remarkably close to the center.
Statistically inevitable.
Right. If you only look at that specific arrow and use the math designed to evaluate a single shooter, you will conclude that the person who shot it is a master archer.
But they aren't.
Exactly, they aren't. They just represent the extreme tail of a massive distribution of attempts.
That is a very accurate way to visualize the shift in the distribution. Because you selected for the extreme, your baseline is completely warped. And this establishes the most important numerical baseline of the paper, that annualized Sharpe of 1.63.
Right.
The authors call this the noise ceiling for a 1,000 trial search.
This means that moving forward, any honest statistical test cannot compare your winning strategy to 0. Beating 0 means absolutely nothing when you've run 1,000 variations.
It's meaningless.
An honest test has to compare your winner to the noise ceiling. It literally has to beat 1.63.
And that leads to the realization that swept through quantitative finance over the last decade. 3 entirely different research programs independently looked at this disaster of false discoveries and arrived at the exact same philosophical conclusion.
Which is?
Stop comparing to 0. Start comparing to what luck produces. But what is fascinating is that they each built a completely different mathematical instrument to solve the problem.
Let's examine the first instrument. This comes from the work of Bailey and Lopez de Prado around 2012 and 2014. It starts with a concept called the probabilistic Sharpe ratio, or PSR, which ultimately evolves into the deflated Sharpe ratio, the DSR.
Right. The probabilistic Sharpe ratio is the first necessary upgrade to the naive test. See, financial returns are almost never perfectly normal.
They don't form a perfect bell curve.
Exactly. They have skewness, meaning they lean to one side, and they have fat tails, meaning extreme events happen much more often than a normal distribution would ever predict.
And the naive test completely ignores this.
It ignores it.
Yeah.
The PSR updates the math to account for the actual shape of your data's returns. It calculates the probability that your true Sharpe ratio exceeds a specific benchmark, but it adjusts the variance of the Sharpe ratio estimate based on the skewness and kurtosis of your specific return series.
Now, the source notes a highly specific detail here about convention. It points out that the math uses a non-excess convention where the normal distribution's kurtosis equals 3.
Yes.
I know it's tempting to gloss over that, but let's clarify why that matters for you guys working in code.
Right.
In a lot of software, when you call a function for kurtosis, it actually returns excess kurtosis, right?
Right, which subtracts 3 so that a normal distribution sits at exactly 0.
So if a researcher takes the PSR formula from the paper, but plugs in an excess kurtosis value from their Python library without adding that 3 back in, what happens?
Oh, the entire calculation just collapses. The variance adjustment becomes fundamentally incorrect, and the resulting probability will be wildly off.
Wow.
It's a subtle engineering detail, but if you get the inputs wrong, the mathematical bridge you were building to protect yourself from false discoveries just crumbles.
Okay, so the PSR gives us a more honest look at a single strategy by respecting the shape of the data. But earlier, we established that evaluating a single strategy is only half the problem, right?
Right.
The real problem is the search itself.
Yeah.
So how does the PSR transition into the deflated Sharpe ratio, the DSO?
The transition happens when we change the benchmark. The PSR allows you to test your Sharpe against any benchmark you choose.
So if you choose 0, you are still falling into the trap.
Exactly. The deflated Sharpe ratio evaluates the PSR at a benchmark that is dynamically set to the expected maximum Sharpe of your entire search.
How exactly does it dynamically calculate that expected maximum? Because we aren't just guessing that it's 1.63 for every search. If you test 100 things, the ceiling is lower. If you test 10,000 things, the ceiling is obviously higher.
Much higher.
So how does the DSR figure out where the bar should be?
It uses extreme value theory, or EVT. This is a branch of statistics specifically dedicated to modeling the extreme deviations from the median of probability distributions.
Okay, EVT.
Think of it as the math used to predict the height of 100-year floods or the maximum wind speed of a hurricane over a decade. EVT provides a theorem that allows us to approximate the asymptotic distribution of the maximum of a sequence of random variables.
Let's try to visualize that. If we are pulling random variables from a bell curve as we pull more and more, the maximum value we've seen obviously goes up.
Yes.
But it doesn't go up in a straight line, right? It slows down.
Exactly. It slows down. As you move further into the tail of a normal distribution, the probability of finding an even larger value drops exponentially. So the maximum grows, but at a decreasing rate.
And EVT captures this behavior.
It does. To calculate the expected maximum Sharpe, the DSR formula takes 3 main ingredients. First, it looks at the total number of trials, n.
Yes.
Second, it calculates the variance across all n of your trial Sharpes. It needs to know the dispersion, how wide the spread of results is that your specific search naturally produced.
Got it. And the third ingredient?
The third ingredient is the Euler-Mascheroni constant.
The what?
The Euler-Mascheroni constant, approximately 2.5772.
Okay, where does that come from?
This constant naturally emerges when you calculate the mean of a Gumbel distribution, which is the specific extreme value distribution that applies to the maximum of normally distributed variables.
Okay, I see.
By combining the number of trials, the variance of the trial outcomes, and this constant, the EVT framework elegantly pinpoints exactly where the noise ceiling sits for your specific parameter suite.
Once it calculates that expected maximum, let's say it calculates our 1.63, it plugs that number into the benchmark slot of the PSR.
Exactly.
It then asks, given the skew and kurtosis of this winning strategy, what is the probability that its true Sharpe ratio is greater than 1.63? And if the resulting DSR is greater than or equal to 0.95, it declares a real discovery.
That is the complete mechanism of the first tool. It sets a dynamic bar based on the math of extremes.
Now let's move to the second approach. This is the Harvey-Liu haircut from 2015, and this completely abandons extreme value theory.
Completely.
It doesn't try to model the distribution of the maximum at all. Instead, it relies on classical multiple testing p-value adjustments.
Harvey and Liu look at the problem through the lens of controlling the false discovery rate directly. The logic is quite simple. If you run 1,000 tests, you are artificially increasing your chances of finding a false positive.
Right.
Therefore, we must penalize the p-values of your results to compensate for the amount of searching you did.
The most famous version of this is the Bonferroni correction, right? If I have a p-value of 0.01, but I ran 100 tests, Bonferroni says I have to multiply 0.01 by 100, which gives me a new p-value of 1.00.
Right.
My significance completely evaporates. It's incredibly blunt.
It is notoriously blunt because it guarantees control over the family-wise error rate, meaning it strictly controls the probability of making even one single false discovery across all your tests.
There's also a slightly more refined version called the Holmes step-down method.
Yeah, Holmes is uniformly more powerful than Bonferroni, meaning it's slightly less likely to kill a true signal, but it operates on the same rigid philosophy.
But the paper focuses heavily on a third method under this umbrella, the Benjamini-Yacuteleli method, or BHY. Why is BHY the preferred tool here?
Because of the reality of how tests behave. Bonferroni assumes the worst-case scenario. BHY is designed to control the false discovery rate under arbitrary dependence.
Arbitrary dependence.
Right. In a parameter grid, your tests are not perfectly independent coin flips. Some are highly correlated. BHY attempts to account for this complex web of dependence, but it charges a heavy mathematical toll for this flexibility.
The paper quantifies that toll, actually. For a 1,000 trial search, the BHY method applies an inflation factor of exactly 7.49.
That means it doesn't just multiply your p-values, it fundamentally shifts the threshold of what is considered significant. It is a severe penalty to ensure that whatever survives the adjustment is genuinely robust.
And the way Harvey and Liu suggest presenting this is brilliant for practitioners. They translate that complex p-value penalty into a haircut.
Yes, the haircut?
Here's how it works conceptually. You take your original, seemingly amazing Sharpe ratio of 3.9. You calculate its naive p-value. You apply the severe BHY penalty to that p-value. Then you reverse engineer the math.
Right, you work backwards.
You ask, what Sharpe ratio would I need to produce this new penalized p-value if I had only run a single test? You compare that new lower Sharpe to your original 3.9, and the difference is your haircut.
It visualizes the invisible toll of the search. If you get a 100% haircut, the math is telling you that 100% of your performance can be attributed to the luck of the search.
Your strategy has been shaved down to the scalp.
Exactly. If you get a 20% haircut, the strategy takes a hit, but the core of the signal survives.
So we have the DSR dynamically raising the benchmark, and we have Harvey Liu applying a severe haircut to the significance. Both of those rely on some theoretical math, either extreme value theory or classical error rate controls. Tool number 3 takes a radically different approach. This is White's reality check from the year 2000, which was later refined into Hansen's SPA, the test for superior predictability, in 2005.
This third approach makes absolutely zero distributional assumptions. It doesn't assume your returns are standard normal. It doesn't use EVT to guess the maximum. It doesn't apply arbitrary penalty multipliers based on the number of tests.
So if it doesn't use theoretical math, how does it know what the noise ceiling is?
It uses brute force computational power to simulate the noise ceiling directly from your own data. It uses a technique called bootstrapping.
Let's do a deep dive into the bootstrap, because the specific type of bootstrap they use, the stationary bootstrap, is critical to why this works.
It is.
If you just take standard bootstrapping, you are essentially putting all your daily returns into a bag, shaking it up, and drawing them out one by one with replacement to create a new simulated history. But if you do that with financial data, you destroy it, right?
You destroy the serial correlation. Financial markets have memory. Today's volatility is highly correlated with yesterday's volatility. If you are in a regime of high volatility, it tends to persist.
Yeah, that makes sense.
If you shuffle individual days like a deck of cards, you obliterate that structure. You create a completely artificial time series that doesn't reflect the reality of how markets move.
I picture it like taking a feature-length movie and cutting it up into individual single frames of film.
Right.
If you shuffle those millions of frames and play it back, you just get chaotic, flashing noise. The story is completely gone.
That is an excellent analogy.
So if you want to simulate a new movie that still feels like a movie, you can't shuffle frames. You have to shuffle entire scenes.
Exactly. That is block bootstrapping. Instead of drawing single days, you draw blocks of consecutive days. But there is a catch.
What's the catch?
If you use fixed-length blocks, say exactly 10 days long, you introduce an artificial periodicity. Every 10 days, there is a jarring, unnatural cut in your simulated data. The math will pick up on that artificial rhythm.
The jump cuts ruin the illusion. So how do White and Hansen fix the jump cuts?
They use the Politis-Romano method, which is the stationary bootstrap. In this method, the length of the blocks is random.
Wait, random block lengths?
Yeah, exactly. It is determined by a geometric distribution. Sometimes you draw a block of 2 days, sometimes 15 days, sometimes 50 days. By randomizing the block lengths, you preserve the internal memory of the time series within the blocks, but you smooth out the transitions so you don't create an artificial heartbeat in the data.
So they use this stationary bootstrap to generate thousands of alternate histories. And by centering those histories around zero, they enforce the null hypothesis. They create a universe where your strategies definitively have no edge.
That's right.
Then they take all 1,000 of your rules, run them over these alternate histories, and record the maximum performance achieved in every single simulation.
Exactly. They build an empirical distribution of the expected maximum by brute force. Your final p-value is simply the percentage of those simulated maximums that manage to beat the actual real-world performance of your winning strategy.
So if your strategy beats 99% of the bootstrapped maximums, you have a p-value of 0.01.
Precisely.
The paper notes one more vital engineering detail about their implementation of this. They use what's called a studentized reality check.
Yes, studentization means they don't just look at the raw mean return of the rules. They divide the mean return of each rule by its own standard error.
Why is that necessary?
Because if you don't do that, the maximum function of your bootstrap can be hijacked by a single terrible strategy that just happens to have massive, wild variance. A strategy that swings wildly between making 50% and losing 50% might accidentally post a huge raw return in one specific bootstrap simply due to volatility, not edge.
Right.
By dividing by the standard error, you force the bootstrap to look for consistent risk-adjusted edge, neutralizing the noise generators.
The paper points out that this studentized approach is slightly different from the full consistent recentering algorithm found in Hansen's SPA, but functionally, in this context, it accomplishes the same goal of stabilizing the variant.
It does, yeah.
So we have three incredibly sophisticated tools. We have the DSR building a theoretical EVT ceiling. We have the Harvey-Liu haircut imposing a multiple testing penalty. We have the reality check physically simulating the ceiling through stationary block bootstrapping.
And now we calibrate them.
Yes, we take these tools and we throw them into the exact same trap we set up in the beginning. We rerun the 2,000 independent searches of 1,000 pure noise strategies.
Remember, because every single strategy is literal static, any discovery flagged here is a failure of the test.
The false discovery rate should be 0, but we allow for an alpha of 0.05, meaning we accept a 5% error rate just due to the limits of statistical confidence.
The results are a stark validation of the math. As we know, the naive test fails completely, giving a false discovery rate of 1.000.
100% failure.
And the deflated Sharpe ratio?
It drops to a false discovery rate of 0.001.
Wow. And the Harvey-Liu haircut using the BHY method?
0.007.
White's reality check?
0.002. All three advanced methods crush the false discoveries, keeping the error rate well below the 5% threshold. I'm looking at the data table from the paper, though, and there is an anomaly that I really have to challenge.
Oh, sure.
It lists the Harvey-Liu method using Bonferroni and the Harvey-Liu method using Holm. For both of them, the false discovery rate is exactly 0.057. First of all, 0.057 is technically above the 0.05 alpha limit.
True.
But more importantly, if Bonferroni and Holm are two different mathematical approaches to multiple testing, why do they produce the exact same number? If they do the exact same thing, isn't it redundant to list them as two different tools in this context?
That is a very sharp pushback, and you are absolutely right to call out the redundancy in this specific application. They are different methods when you are evaluating the entire set of 1,000 hypotheses.
Okay.
Holm is a step-down procedure. It sorts the p-values and evaluates them sequentially. Bonferroni just applies a blanket penalty to everything.
Right.
However, the first step of the Holm procedure, evaluating the single smallest p-value, which corresponds to our maximum strategy, is mathematically identical to Bonferroni by construction.
Oh, I see.
Because we are only asking these tools to evaluate the single best strategy out of the search, they are executing the exact same mathematical operation. The results match perfectly because it is one confirmation, not two.
Okay, that clarifies the redundancy. But what about the 0.057 itself? If we set an alpha of 0.05 and the test yields 0.057, didn't it fail to control the error rate?
It didn't fail. We are observing the limits of a finite simulation. We only ran 2,000 searches.
Right.
In Monte Carlo simulations, your empirical result has a standard error. For a true probability of 0.05 measured over 2,000 trials, the standard error is roughly 0.005.
Right.
So an observation of 0.057 is only about 1.4 standard errors above the target.
Mm,
Statistically speaking, it is well within the expected margin of noise for a simulation of this size.
gotcha. So if we ran 2 million searches, it would converge tightly to 0.05.
Exactly.
That makes perfect sense. Now, out of all these calibration numbers, there is a metric hidden in the background of the DSR calculation that the authors highlight as profound. When they looked closely at the SSR dollars, the expected maximum benchmark that the extreme value theory dynamically calculated across all 2,000 of those null searches, they averaged it out.
And the average dynamically calculated bar was exactly an annualized 1.63.
This is the moment the whole theoretical framework just locks together. The DSR's internal dynamic mathematical engine independently arrived at the exact same noise ceiling that we empirically observe when we brute force the max of 1,000 pure noise trials.
It works.
It really does. The DSR does not ask the winner to beat 0. It asks the winner to beat the best score luck alone can produce. If your strategy merely matches the noise ceiling of 1.63, your DSR score will sit right around 0.5, which is a coin flip.
Right. To actually be declared a discovery and push the DSR past 0.95, you have to definitively clear the 1.63 ceiling.
It's a beautiful mathematical symmetry, but a test that is perfect at rejecting noise is only half of the equation, right?
Definitely.
Let me play the skeptical practitioner for a moment. It is very easy to build a statistical test that rejects false positives. I can just write a piece of code that says reject everything and it will have a false discovery rate of 0.
Well,
But a totally paranoid system is also completely useless. What happens when there is an actual real money-making edge hidden in the data? If I find a real signal, do these advanced tools kill the golden goose because they are too strict?
this is the concept of statistical power. The probability that a test correctly rejects the null hypothesis when a true alternative exists. To measure power, the researchers design a new experiment.
Okay, what do they do?
Out of 1,000 strategies, they plant 25 that have a real, mathematically genuine edge of known strength. The remaining 975 are still pure static noise. They run the search, and they sweep the strength of that planted edge from very weak to very strong, tracing how the DSR responds.
So they trace what we call an S-curve. Let's walk up this curve to see how the DSR behaves. We start at the bottom, below the noise ceiling. They plant a true, real annualized Sharpe of 0.79.
Right.
Again, this veg is real. It is not noise. But when they run the DSR, it only fires and calls it a discovery 0.5% of the time. Now, on the surface, that looks like a failure. The tool missed a real signal 99.5% of the time. Isn't it failing if it misses a real signal?
No, it is actually functioning perfectly. You have to think about the signal-to-noise ratio of the environment.
Okay.
The noise ceiling of this 1,000 trial search is 1.63. The luckiest noise strategies are routinely posting Sharpes of 1.63. Your real edge is only generating a Sharpe of 0.79. In this specific search space, a 0.79 signal is physically indistinguishable from the noise. It's completely buried.
I see.
Pretending you can mathematically isolate a 0.79 signal from a sea of 1.63 noise using only in-sample data is dishonest. The DSR correctly refuses to call it a discovery because there is not enough evidence to differentiate it from luck.
It's like standing in a stadium full of screaming people, and someone on the other side of the field whispers a secret code. Even if the whisper is real, if you claim you heard it over the roar of the crowd, you are just lying to yourself.
Exactly. The test is protecting you from hubris.
So, when does the test finally start hearing the signal?
The curve begins to climb right around the noise ceiling. When the true Sharpe of the planted edge is pushed to 1.27, the detection power rises to 9%. When it hits 1.90, which is just above the 1.63 ceiling, the power jumps significantly to 65%.
The paper provides an interpolation here that is so satisfying. The exact 50% power crossover, the exact point where the DSR catches the real edge half the time and misses it half the time, sits at an annualized Sharpe of about 1.73.
Which logically makes perfect sense. 1.73 is just above the 1.63 noise ceiling. It is the precise moment the signal finally outruns the noise generated by the search.
And as the edge gets stronger, the power approaches near certainty. By a true annualized Sharpe of 2.54, the detection power is barely 998. By 3.17, it's a perfect 1.00. It catches the real edge every single time. And throughout this entire sweep, false positives flagging one of the 975 noise strategies stay pinned essentially at 0.
The contrast with the naive test here highlights a fundamental philosophical difference in data science. The naive test will detect that weak 0.79 edge 67% of the time.
Because the naive test detects everything. A test
Mhm.
that fires on everything has no discrimination. A broken clock is right twice a day, but you don't use it to time a race.
Right.
The DSR willingly sacrifices sensitivity to marginal, weak edges to absolutely guarantee that the discoveries it does flag are genuinely real.
It is a trade-off that prioritizes capital preservation. You would rather miss a weak edge than bet billions on a mirage.
Absolutely. So we have a complete framework. The math is pristine, the calibration is perfect. We just run the deflated Sharpe ratio, beat the EVT noise ceiling, and we are safe.
If we lived in a frictionless mathematical vacuum, yes, but we don't.
This brings us to the practitioner's trap. Up until this very moment, every assumption in the math has relied on one crucial word: independent.
Yes, independent.
We assumed all 1,000 strategies in the search were perfectly independent of each other. But let's look at the messy reality of what analysts actually do. They run parameter grids.
Think back to your opening example, a moving average crossover strategy. 16 fast lengths, 40 slow lengths,
Yes.
640 combinations.
If I test a fast length of 45 and a slow length of 120, and then I test a fast length of 45 and a slow length of 125, I am not testing two independent ideas. I'm testing the exact same idea with a tiny tweak.
Exactly.
The buy and sell signals will overlap 99% of the time. The returns will be nearly identical. The researchers measured this reality. They found the average pairwise correlation of this 640 cell grid is roughly 0.61. These are highly intertwined, heavily correlated bets.
And this correlation breaks the foundational assumption of our pristine math. Extreme value theory needs to know exactly how many independent draws you took to calculate the correct maximum. If you feed it highly correlated draws, the EVT engine starts to misfire.
To expose this misfire, the researchers test the grid in two different scenarios. Case A is the random walk. They run the 640 highly correlated combinations on pure, random data with no edge.
The winning combination, which happens to be fast 45, slow 120, posts an annualized Sharpe of 0.81. Because the underlying data is random, this 0.81 is entirely luck.
And how do our advanced tools handle it? They handle it flawlessly. Even the unadjusted probabilistic Sharpe ratio, just testing against a benchmark of 0, only scores 0.918, which falls short of the 0.95 threshold for discovery.
And the DSR absolutely crushes it. The DSR calculates a deflated benchmark of roughly 0.91. Since the winner's Sharpe is only 0.81, it fails completely. The final DSR score plummets to 0.431. The Harvey-Liu haircut shaves off 100% of the Sharpe. Reality Check rejects it outright. When evaluating pure noise, the system works perfectly, even when correlation is present.
But case A was the easy test. Case B is the twist. This is the genuine regime edge. They run the exact same 640 cell correlated grid, but this time they feed it a regime switching time series.
Okay.
This data contains a real mathematically exploitable underlying edge if you can catch the regime shifts.
And the grid finds the edge. The winning combination posts a massive annualized Sharpe of 3.92. Now, to be rigorous, that 3.92 is an in-sample number. It is inflated by the selection process. But underneath that inflation, there is a true, genuine regime effect driving the performance.
It is a real discovery.
Yes. The single-test naive p-value is that 6 times 10 to the negative 12th we mentioned at the start. The raw, undeflated PSR is a perfect 1.000.
Then they run the raw deflated Sharpe ratio. They plug the winner in, they tell the formula n equals 640, and the result comes back. The DSR is 0.748. It fails the 0.95 threshold. The raw DSR actively falsely rejects a genuine massive edge.
This is the nightmare scenario for a quantitative researcher. You did everything right. You found a real edge, you used the most advanced statistical tool available to verify it, and the tool told you to throw it in the trash.
Why did the DSR break? What went wrong inside the EVT calculation?
It suffered from severe overdeflation. When you explicitly tell the DSR formula that n equals 640, the math assumes you took 640 completely independent shots on goal. Because it thinks you searched 640 entirely separate, uncorrelated ideas, it artificially inflates the expected maximal benchmark. It pushes the noise ceiling up to a staggering annualized 3.51.
That is an absurdly high bar. But it gets worse, doesn't it, because of how EVT uses variance.
Exactly. Remember the second ingredient of EV, the variance across all the trial Sharpes. In this regime switching data, there is genuine skill dispersion. Some parameter combinations are incredibly good at catching the regime shifts, and others are terrible at it. This means the spread of results across the grid is very wide. The variance is high. The EVT formula sees this high variance, blindly assumes it represents wild, independent noise, and pushes the bar even higher as a penalty. So now, your genuine 3.92 winner is trying to jump over an artificially inflated 3.51 bar. It only clears it modestly, which is why the DSR probability collapses to 0.748.
It is essentially punishing you for having a lot of good, slightly varied ideas. If counting the raw grid size of 640 breaks the math, what number are we actually supposed to plug into the DSR for n? How do we fix the formula?
The solution is that we must feed the DSR the effective number of trials, not the raw count. We denote this as N effective. We have to use linear algebra to look at the correlation matrix of our strategies and mathematically estimate how many truly independent bets are buried inside those 640 overlapping combinations.
The paper explores several ways to estimate n effective. Let's start with the most intuitive one, which is based on average correlation. There is a simple formula: you take n and divide it by 1 plus n minus 1 times the average correlation. When you plug our 640 grid and our 0.61 average correlation into that formula, it collapses the grid down to an effective n of just 1.6 trials.
It mathematically argues that out of 640 variations, you only really tested 1.6 independent concepts.
And if we plug n equals 1.6 into the DSR formula, the strategy passes. The DSR jumps to 1.00. But the paper points out a massive fatal flaw with this. If you tell the DSR that n equals 1.6, the EVT math lowers the noise ceiling to an annualized 0.25, which is virtually zero.
You have essentially bypassed the entire purpose of the DSR. By dropping the bar to 0.25, you have turned deflation off. The resulting DSR of 1.00 is just inheriting the raw, undeflated, naive significance. It gives you a false sense of security.
Why is the average correlation formula so wrong?
Because of a fundamental mathematical mismatch. That simple formula is designed as a variance reduction factor for estimating the mean of correlated variables. But remember, the DSR relies on extreme value theory. EVT models the maximum.
Oh, right.
The correlation structure impacts a mean very differently than it impacts a maximum in the extreme tails. It's pointing in the right general direction, telling us n is much smaller than 640, but it is the wrong tool for this specific job.
So we absolutely cannot use 640 because it overdeflates the bar to 3.51 and kills real edges. We cannot use 1.6 because it turns deflation off and leaves us exposed to noise. Where is the defensible middle?
To find the defensible middle, we have to look deeper into the correlation matrix using eigenvalues.
Let's try to conceptualize what an eigenvalue represents in this context because it can sound very abstract. If I have 640 strategies, but they all perfectly move in lockstep every single day, they have the exact same return that is really just one strategy, that is one dimension of variance. An eigenvalue essentially measures how much of the total grid's movement is captured by a single underlying dimension.
That is exactly right. By analyzing the eigenvalues of the correlation matrix, we can ask how many independent dimensions of variance are required to explain the behavior of the grid. The paper details several standard estimators used in genetics and linear algebra to determine this.
Let's look at the band of estimates they produce. First, there's the participation ratio, which gives an n effective of 2.4. Still too low.
Yeah, too low.
Then we look at PCA principal component analysis. If we ask it to keep enough dimensions to explain 95% of the total variance of the grid, it gives an n effective of 16.
Okay.
Then there is the Kaiser rule. This rule simply says we only count dimensions that have an eigenvalue greater than 1, meaning they explain more variance than a single standardized strategy would on its own. The Kaiser rule gives an n effective of 21. Finally, there is an estimator from genetics called Cheveryd-Nyholt, which gives an n effective of 370.
Look at the middle of that band, the PCA and Kaiser estimators. They suggest the effective number of independent trials is somewhere between 16 and 21.
And what happens to the DSR bar when we use 16 to 21 effective trials?
The math imposes a real, scientifically defensible, punishing annualized bar of between 1.85 and 2.00.
That is a serious, rigorous noise ceiling. It is not the artificial 3.51, and it is not the free pass of 0.25. It demands real performance, and the ultimate verdict for our genuine regime edge. The true 3.92 Sharpe clears this defensible middle bar easily. It scores a DSR of 1.000 and 0.999.
The mathematics prove that the edge survives for any effective n below 144.8. It only fails under the raw 640 count and under that massive Cheveryd-Nyholt 370 estimate, which the authors explicitly note provably overcounts when a matrix is heavily equicorrelated.
This reveals the core lesson for any practitioner. Do not anchor on a single lucky number for n. Don't pick the estimator that gives you the exact answer you want. The only honest, robust claim you can make is a verdict that remains stable across the entire band of standard effective trial estimators. If your strategy survives the defensible middle, you have something real.
After
But as we close in on the synthesis of all this, there is a fascinating detail from case B that we have intentionally held back. While the DSR was struggling with the N count, twisting itself in mathematical knots over correlation matrices and eigenvalues to avoid overdeflation, tool number 3 didn't struggle at all. The reality check and Hansen's SPA got the answer right immediately.
They did. When applied to the correlated grid with the genuine regime edge, the SPA type test confirmed the real discovery on the very first try, producing a definitive p-value of 0.00024.
Why? Why did reality check breeze right through the correlation trap that completely derailed the DSR?
Because of the bootstrap. The bootstrap handles dependence natively. Remember, the reality check resamples blocks of the actual historical correlated return streams of your grid. Because it is drawing from the true data, it physically preserves all the tangled, complex relationships between fast equals 45 and fast equals 46.
Wow.
It never has to stop, calculate a correlation matrix, and guess at hypothetical independent bets. It simply reads the reality of the dependence directly from the data.
So the two tools are fundamentally answering different questions.
Precisely. The deflated Sharpe ratio asks an internal question. Is the winner special relative to the specific search space it came from? To answer that accurately, it must know the effective size of that space.
The other.
A reality check asks an external question. Does the best rule in this set genuinely beat cache after we mechanically adjust for the data snooping? It bypasses the need to count trials by simulating the snooping process directly on the data.
So the synthesis here for you, the listener, is that you want to use both. You want to run the DSR across a band of effective trials to understand the theoretical boundaries of your search. And you want to run the reality check block bootstrap to get a non-parametric structural opinion drawn directly from the data itself.
Right.
If the two tools disagree, like the raw count DSR and the reality check did in our regime example, it is a massive diagnostic alarm bell. It means you are mathematically misrepresenting the dependence in your grid. When both tools agree, that is when you can actually begin to trust your winner.
Before we conclude, we must touch on a note of honesty from the source material. The authors are extremely transparent about why they structured the study this way. The returns they used were entirely synthetic. They used pure independent normal noise, and they used cleanly planted regime switching data.
Right. They deliberately did not use messy, real-world S&P 500 tick data.
And they did that because they needed absolute, unquestionable ground truth to calibrate these tests. If you apply a new test to real market data, and the test rejects your favorite strategy, you are left with an unresolvable doubt. Is the test too strict, or did the strategy just lack a real edge? By using synthetic data where the presence or absence of an edge is a literal mathematical fact encoded into the simulation, they definitively prove that the methods work.
I view it like testing a metal detector. You don't test a brand new metal detector by walking into a random public park and hoping you find something.
No, you'd never know if it was working.
Right. You test it in a controlled laboratory sandbox where you know exactly where the gold coins are buried and you know exactly where there is only dirt. You calibrate it in the lab so that when you finally take it out into the messy real world, you can trust its signal.
That's a perfect analogy.
Let's synthesize this massive paradigm shift we've explored today. A parameter search is not an experiment. It is a multiple testing machine. It is an engine explicitly designed for generating extreme luck.
Yes.
The standard naive p-value that your software spits out by default is fundamentally broken in this context. It will vouch for pure, unadulterated noise with absolute, unshakable confidence 100% of the time. Therefore, the winner of any parameter sweep must be considered mathematically guilty until proven innocent.
The actionable takeaways to prove that innocence are clear. First, deflate your benchmark. Do not compare your winner to zero. Compare it to the noise ceiling that extreme luck naturally delivers.
What's the second?
Second, if you are running a correlated parameter grid, count your effective trials honestly by reading across a band of eigenvalue estimators, not just the raw count. And third, use a stationary block bootstrap to simulate the data snooping process for a second, structural opinion.
What survives all three of those rigorous checks might actually be a real discovery. What clears only the naive standard statistical test is nothing more than the tallest person in a room of 1,000 coin flippers.
Exactly.
We have covered immense mathematical ground today, and I want to leave you with one final lingering thought. We just spent this entire deep dive dissecting quantitative finance, an environment where the data is clean, the rules are perfectly mathematical, every decision is logged, and the feedback loop is immediate.
And even in that pristine environment, selection bias can perfectly manufacture a genius-level Sharpe of 1.63 out of literal thin air.
So, consider the rest of the world. How much alpha in human decision-making, how many brilliant corporate business strategies, or even successful medical trials are just the undeflated winners of massive invisible parameter sweeps that we didn't even realize we were running. Thank you so much for joining us on this exploration. Keep questioning your winners, and we will see you on the next deep dive.